hello. So this is a big digger. It's called Bagger 288, and it can dig through a lot of dirt. And we've built some machinery around Postgres and other things that can also dig through a lot of data, which is why we also called it Bagger. So about me, I'm just a sysadmin. I don't really know a lot about databases. I don't particularly care much about Postgres either, but it's very good at solving our problems, so we use it. And if there was something better, we'd use it, but there isn't, so Postgres it is. So at Adjust, I've been told that we're known at the Postgres community for being the place that does a lot of custom data types. I guess soon we'll be known as the place that turns off vacuum. We do mobile analytics. We produce loads of data points. Well, our users produce loads of data points. And we don't use cloud, except for a few test systems, because it would be too expensive. We run everything on bare metal. And our machines run Gen 2. So we've had an Elasticsearch cluster. We kept it as a big event log. We don't keep the data forever. We expire it after some time. At the end of the cluster's life, it had 1.3 petabytes of data, and it was more or less unusable. Our problems with Elasticsearch was that it's unscalable. Past the petabyte mark, there is just so much crosstalk, and it uses so much, mostly network, just to keep up with itself, keep all the nodes synchronized, that you can't query it. Because you send it the simplest query and it just times out because the query never has the time to execute because the cluster is busy just being alive. And try running the JVM at about 100 gigabytes heap. Your GC pauses are about 1 minute. And that's enough for that node to just go offline and never, ever come back. So we basically had about 50 servers, very beefy, expensive machines that spend a lot of network time and didn't do anything useful. So we started building Bagger. We put the Bagger cluster online about just over a month before this date, and we've run them both in parallel. And the reason for this is because we wanted to gather enough data in the Bagger cluster, and also we wanted to train our users to be able to use the new tool. And on the 4th of August 2017, we just turned off Elasticsearch and got quite drunk. So Bagger is not an exact replacement for Elasticsearch. It's just tuned for our exact use case. It's still just an event log. It tags every single incoming event and just stores it in more or less Postgres. So this is the basic stack. Redis is not really used anymore, and what keeps it together is Shuffle. Shuffle means shovel, and that's a big shovel that can move quite a bit of dirt, and Shuffle just takes a pile of data and throws it into another database. And it's basically this, but for databases. It can, for example, convert, it can be a producer from Kafka, produce into Kafka, or consume from Kafka and write into Postgres, vice versa, Redis, etc. So I'll just mention how our data works. Events come in from mobile devices. when it comes into our backend, it gets timestamped and has a tag and a source name. They're grouped by 1 hour, and that's our partitions, and we just delete them after several days, usually about 30. It doesn't really matter much if we lose part of the data set, and if it comes in late, it's also not a problem, so we can just forget about those issues. If we lose a bit of data, it's not a big problem. I'll just mention that we're getting rid of Redis from the stack, but for the sake of completeness, it was there, but we want to not use it because it's too slow. It can do maybe 100,000 inserts per second, but past that, it just dies. So the way we use Kafka is just a big buffer. It can have multiple producers and multiple consumers. And thanks to Kafka, we don't need to worry about anything at night. If something goes down, we just go back to sleep. In the morning, we fix it. Kafka can queue up massive amounts of data, and it's pretty fast. Even despite running on the JVM, it's pretty okay. And then connected to Kafka, we have a cluster of shuffles. They're running in pairs, so that one of them can go down at any time, and then the other one can pick up. It copies the stream from Kafka into Postgres. Whenever there's a new event, it just picks up the next event and sticks it into whatever Postgres it has connected to itself. Because of this, we don't need to worry so much about any particular pair going down, because then another pair will just pick up the slack, and it will be just slightly slower at consuming, but we have enough capacity, so it doesn't matter so much, and then we can just fix. Each shuffle then writes into its Postgres. The Postgres and the shuffles run on the same machine. We have about 30 of them. They're pairs, so that if one goes down, there is no reduction in capacity. If two go down, then Kafka will automatically redistribute the events into the machines that are available. We partition the events into one table per hour, but each pair of Postgres has its own set of tables, which means that events from one particular hour can end up in on multiple machines. So we don't do vacuum. There's no need to do vacuum because the load is entirely append only, so the vacuum wouldn't clean up anything anyway. And the way we clean up is that every hour there's a cron job that just deletes expired data. There's no need to have vacuum. So there's some bookkeeping machinery. The master database just keeps track of what's available and what's down. Things that are down are never queried. Things that are not down are queried whenever a query comes in. All the events are grouped into generations. So a generation is basically a set of tables for a particular hour, because there is multiple tables per hour, because each table is on its own Postgres. And the events are partitioned by those hours and then just stuck into individual tables. We do nothing fancy, it's just tables and sets of tables. So far, you know how an event comes in, it gets put into Kafka. From Kafka, one shuffle picks it up and sticks it into its Postgres. So we have, after an hour, a bunch of events and a bunch of machines, and that's still not very useful, because what about taking the data out? What's the use of a database if you can't query it? So we wrote a Perl script It's a simple command line tool. It takes the service name that that an event has possibly been tagged with, a time range, and possibly a key. Asks the master database for the partitions that might have that event, runs an explain, and then rejects possible sequential scans. This is because sequential scans are really costly, and we don't want users running sequential scans. Bitmap scans are okay, but sequential scans are no. If somebody writes a query that requires a sequential scan, we just refuse and tell them, please make a better query. We've trained our users how to avoid sequential scans, so they know how to not trigger them. And the users are not very technical, but they're getting better. After we've figured out that it's not a sequential scan, we just run the query, and we run the query on each partition, and then gather all the data together. And it's kind of like MapReduce in the sense that we run a query in parallel on multiple databases and then combine the results together. So how does it work out? It works out pretty well. We've managed to reduce the size of the cluster. And now it has even more data in it because every month we have more data points. We have the wall on SSDs. That makes things pretty fast. And the data is compressed, and the compression ratio is pretty good. Most of it is data. There is still quite a lot of metadata around, but that keeps things fast. So we have about 2 million partitions, and that number changes all the time depending on how many events there are. Spread across 240 instances, and this whole machine can do about 1 million inserts per 1 second. And so the one great thing about this is you can use it for testing any sort of new database tag. Because if we lose one pair of data from one pair of Postgreses, it doesn't really matter so much. We can afford it. This data is not very important. Well, it is important, but it's not important that we keep all of it at all times. Would be very happy to hear about if you wanted to test your maybe new storage engines or compression or anything else. Send us your test cases, and then we can run them. You can see how they keep up, and there are 1 million inserts a second in a petabyte-size cluster. Maybe they just fall down, and we tell you that you need to fix something, and maybe you have a nice data point. You can tell your clients, look, we've tested it on a petabyte-size cluster with 1 million inserts per second on production scale traffic, and it kept up just fine. And the important thing to take away from this is that there's no need to be stuck with something you're unhappy with. We're very unhappy with our Elasticsearch cluster. The cluster was big, expensive, and completely useless. So we just went away, spent some time designing a new, something new that would replace and do something that we could be happy with, and something that did exactly what we wanted. We knew how to grow it. We knew that it's scalable because we've seen Postgres scale basically without end. So we just did it. And we didn't ask anybody if we can. We knew we can, so we just did it. And you should do the same. If your work says, no, you must be stuck with this tech, just be bold. And worst case, you quit your job. And you can come work with us on a petabyte-sized clusters if you like. So thank you. If you have any questions, please ask in English. If you prefer to ask it in Russian, you can do it after the talk. I have my friend who translate.
I have two small questions. First, what type of GC you use in Elasticsearch? It was new GC or G1 GC?
As far as I can remember, we've tested both, and none of them could keep up.
Okay, and the second question, what can you explain your mappings and your Elasticsearch? Can you some example maybe? What schema of saving data in your Elasticsearch?
So we've ended up in a more or less similar format, but each document was basically just JSON, and we tried to do the whole NoSQL thing and not have a defined schema and use it like what it was meant to be, and it just didn't work very well. In Postgres, we don't have a very set schema either. We store documents as JSON as well, but we keep the metadata in a schema, and that helps a lot because then we can fetch it easily.
Thanks for the interesting talk. My question is about vacuum. You said that you didn't need vacuum because your tables were insert only.
Append only, sorry.
Yeah. Does it mean that you did not use index-only scans in your queries, or did you insert it using copy freeze? You see, index-only scans don't work without tables being regularly vacuumed, even if they are append-only.
Right, but the thing is, we don't keep tables around for a long time. So we don't need to yeah, well, okay, so Chris is telling me we analyze directly, so yeah. So just come back after the talk,
will
and I'll explain.
Will do, thank you.
Okay.
Hello? I'm not sure if my question is relevant, but your talk is called How We Migrated 1 petabyte of data, and you were talking about Postgres and configuration, but I haven't heard anything about migration process. Which tools were used? How long does it take? Did you bring system down? How you ensure the continuous of operation?
Okay, so maybe I should have explained it a bit more in detail. So what we did is we run the two clusters in parallel. They were both receiving the same data for about a month and a bit, at which point we've satisfied the retention criteria, and we could just turn off the old cluster. So we filled them up with the same data, and then once they had the same data, we could just turn off the old one.
You did not move data out of Elasticsearch to Postgres physically. You didn't, did you?
No.
Okay.
You don't use vacuum, but you drop tables.
Yes.
So how you handle with system tables, PG class, PG attribute, when you drop tables, data from system tables doesn't disappear. So system tables can bloat.
I don't think we vacuum system tables, but we just might. I was talking mostly about the actual data tables. For vacuuming system tables, we might want to just stop a pair of nodes and then do a manual vacuum from time to time, because we have 30 pairs, so we can take one down anytime, and that's no reduction in capacity. So we just take down for maintenance and do everything by hand in a way.
Okay, thanks.
Thank you for your presentation. And the question is, could you tell more about your master database? It consists of records that points to the partitions or servers
Yes.
that house the partitions?
How are the partitions made?
No. What looks like master database? It's a table, simple table that points that data from yesterday stored in partition 1. Partition 1 says on server 1 or something else. More details.
Yes, more or less like that. Yes, it's just a table, and in that table we group. We have a row for each generation and partition, and they're just called by the service name, the tag name, and the timestamp, the hourly timestamp. And
Okay.
it's just a list of those partitions.
Okay, clear. You said about you run your Postgres in pairs. Obviously, this is master-slave, yeah?
Yes.
Okay. How do master database knows about that one node is down? You switch to slave, and how master database knows about it? And
So there's two things here. As far as consuming from Kafka, the incoming data, that just handled automatically by Kafka because there's fewer consumers. And there's fewer consumers, so that's handled automatically. As far as for querying goes, if we just open connections and check if a database is running. So we just keep track of which databases respond, and if they don't respond, we just mark them as down and don't query them until they come back up.
okay, thanks.
Okay, Wiktor, thank you for your interesting talk. Let's thank Wiktor.
Okay, thank you.